This is Randall Schell, and I'm making a podcast on anesthesia machine topics, specifically on published keywords related to the anesthesia machine between 2007 and 2015 as a precursor to our flipped classroom interactive session. So if we look at the 2007 to 2015 published keywords on machine topics, I've broken down them into 5 categories. The first category is cylinders and gas supply, things like the E-cylinder pressures and volumes of gases and the relationships between pressure and volume of gases in E-cylinders, both nitrous and oxygen. Wall oxygen failures and what's the sign of it, what do you do about it. Pin index and the diameter index systems, inspiratory and expiratory valve dysfunctions. Related to vaporizers, there's questions about vaporizer output and factors affecting them, what happens at altitude, des-flaring vaporizers versus flow-over variable bypass vaporizers. The CO2 absorber, some issues with volatile anesthetic toxicity and carbon monoxide and exhaustion or drying out of the soda lime. And then some miscellaneous machine and circle system topics like flow meters and rotameters and waste gas scavenging, as well as others. So let's move right on to compressed gases in E-cylinders. Oxygen is supplied in an E-cylinder at approximately 2,000 psi as a full tank, and there is 660 liters of oxygen in that full tank. It is a non-liquefied gas, and as the gas is used, the pressure decreases steadily with emptying of the cylinder. And at approximately 1,000 psi, or half of a tank, there is half of the volume of gas left, half of 660 being 330 liters. Nitrous oxide is supplied at 750 psi with 1,590 liters of gas. It is a liquefied gas, and the pressure in that tank will remain constant until all of the liquid has turned to gas, and then it begins to drop as the cylinder is emptied. When it first starts to drop from that pressure of approximately 750 psi, there is only about 20% of that gas left, or approximately 400 liters or so of nitrous oxide. But again, the pressure does not drop until the tank is about 75% empty, and for you to know how much gas is left in that nitrous cylinder, you would have to weigh the cylinder. So up at the top is a representation of the oxygen dropping off pressure as the gas is used, as opposed to the nitrous oxide tank, the pressure staying the same until approximately a fourth of the tank is left. Liquid is used up and the gas is being used at that time. The concept of critical temperature and pressure is important to the understanding of why the gases are supplied as they are. Critical pressure refers to the minimum pressure that causes liquefaction or moving of a gas to a liquid state at its critical temperature. And the definition of critical temperature is the temperature above which a gas cannot be liquefied no matter how much pressure you apply to it. So the critical temperature of nitrous oxide is about 36 degrees centigrade, and that means that if you get above that temperature, no matter how much pressure you apply to nitrous oxide, you cannot get it into a liquid state. But the temperature of nitrous oxide in the operating room is not 36 degrees, it's much less than that, so it can be liquefied as pressure is applied to it. The critical temperature of oxygen is a minus 118 degrees centigrade. Because we cannot provide a minus 118 degrees centigrade temperature to the cylinder in the operating room, it cannot be liquefied at OR cylinder temperatures. So oxygen is a gas, nitrous oxide supplied as a liquid gas mixture. Wall source oxygen failure or crossover gas issues. If you believe that the gas coming from the wall source, there's something wrong with it, you should turn on your backup oxygen cylinder on the back of your tank and disconnect the pipeline supply, the DISS or diameter index safety system pipeline supply. Why do you have to disconnect at the same time that you're turning on your oxygen cylinder? Because the machine will preferentially use the gas coming from the higher PSI, that is the pipeline supply source, which is at about 50 PSI, rather than from the tank, which is 45 PSI. And if what was coming from the wall source had a pressure of 50 PSI, but it wasn't oxygen, there was a crossover gas failure, you would preferentially supply that gas to the patient rather than from the tank. So turn on your tank and disconnect the oxygen wall source. Pressure regulators. Cylinder gas, you would not want to supply a pressure of what the oxygen tank is or what the nitrous tank is to a patient. You would blow their lungs. So you have to have regulators that reduce the cylinder gas pressure, and it does so to pressures of approximately 45 to 47 before it enters flow valves. This is slightly lower than the pipeline supply as previously discussed, and allows preferential use of the pipeline supply rather than the cylinder. So if you leave your cylinder gas open, as long as you have a pipeline supply coming, you should not be using the cylinder gas. You should be using the pipeline gas. The pipeline gas supply is delivered to the anesthesia machine at 50 psi, slightly higher than the cylinder gas is regulated at. Some machines use a second regulator to drop the pipeline and cylinder pressure even further, two-stage regulator down to 12 to 19 psi to the oxygen flow meters. We talked about if we lose oxygen pipeline pressure, or there's, I believe, a crossover gas issue, we said to open the oxygen cylinder, fully disconnect the pipeline connection at the wall, hand ventilate the patient, and consider using another oxygen cylinder source if you're really worried, and an ambu bag if necessary. Your APR valve or pop-off valve is another pressure regulator to some extent. It limits the pressure that can be built up in the circle system when you're hand ventilating, and the upper limit is usually about 70-80 centimeters of water. There is risk of barotrauma as that pressure goes up to that level, and if thoracic pressure rises and venous return decreases, there could be hemodynamic compromise and drop in blood pressure. So if you look at the pressure in the anesthesia machine, you can see that there is the low pressure side on the right and the high pressure side on the left. And the low pressure side is from the flow meters down to the machine outlet to the patient. Notice that the oxygen flush valve is outside that low pressure circuit. The oxygen pipeline source, we said, is 50 psi, while the cylinder source is a little bit less than that, regulated at about 45 to 47 psi. So once again, as long as your pipeline supply is coming in at its normal pressure, gas will preferentially be used from the pipeline supply. Gas flow concepts and rotameters. From the physics of gas flow, you probably remember that flow through a tube is laminar and dependent upon viscosity. And the way I like to remember that is TV, tube viscosity, while flow through an orifice on the top right is turbulent and dependent on the density of the gas. And the clinical application of that is using helium as one of your gases to breathe in a patient with, for example, subglottic stenosis that's very tight. It reduces turbulence and flow increases through an orifice. So once again, flow through a tube is dependent on viscosity, TV, while flow through an orifice is dependent upon density. Now, what's the application to rotameters or flows, control meters? Well, at low flows, the bobbin is near the bottom of the tube, and the bobbin and the wall of the flow meter act like a tube. And so gas flow is laminar, and viscosity, tube and viscosity, are important. And as flow rate increases, the bobbin rises up the flow meter, and the gap increases between the bobbin and the side of the flow meter. It begins to act like an orifice, and density of the gas actually affects its flow. One of the take-home messages is that bobbins and flow meters are specific to each gas and machine. We can't exchange flow meters, and even graduations on the flow meters are not uniform, so don't attempt to change them out between machines. Oxygen supply flush valve is the next topic. When you hit the oxygen supply flush valve, you are supplying high flow of gas, somewhere around 50 liters per minute, directly to the common gas outlet at a line pressure of approximately 45 to 55 psi. So here is our oxygen supply valve at the bottom of the figure. When you press that in, about 50-50, 50 liters of flow at about 50 psi goes to the patient. And notice that this is bypassing the flow meters and bypassing the vaporizers. So 100% oxygen is being supplied to the patient without any inhaled volatile anesthetic if you were using it. So it's going to dilute the inhaled volatile anesthetic in a patient. And if you continue to press that flow meter or that oxygen flush valve, you can dilute out the anesthetic and you may actually have awareness in a patient. That's one risk. Notice that if you're using a cylinder source, you still will not bypass the first stage regulator when you press on that oxygen flush valve. You sure wouldn't want to supply the pressures that are present in the oxygen and the nitrous cylinders, 750 and 2000 approximately, directly to a patient's lungs, but it still goes through a first stage regulator. There is a risk of potential barotrauma also when you hit the flush valve. So two potential issues with the supply flush valve: when you press it down and continue to press it down, you can get barotrauma and you can dilute out a volatile anesthetic if you're supplying it. Let's talk about inspiratory and expiratory valve dysfunctions now. Up at the top right, you can see an inspiratory valve that has slipped off its normal position and would not be functioning normally. The expiratory valve is on the opposite side here on the right. So if the inspiratory valve happened to be stuck in a closed position and you had a competent expiratory valve, then you can't deliver a breath to the patient. Squeezing the bag, whatever, and as you squeeze the bag, you can't get air in. Just remember that if you're having problems with your machine and your circle system, one of your backups is to remove the patient from the anesthesia machine, hook up an AMBU with an oxygen source, and hand ventilate the patient until you can figure out what the problem is. More common with the inspiratory valve, however, is failure to properly close, and it's just leaky or partially open during expiration, meaning that CO2 will go back up the inspiratory limb of the circuit and with the next breath be rebreathed. So rebreathing, as evidenced by elevations of baseline end tidal CO2, will be present. And if you look at the red vertical line here, you can see at the end of expiration, at the beginning of inspiration, notice that there's carbon dioxide in it and you don't have the normal square waveform, but a sloping off of that CO2 curve, indicative of an inspiratory valve malfunction, and the baseline being up, evidence of rebreathing. What you can do in this situation is increase your fresh gas flow, i.e. from 1 liter per minute if you're flowing that, up to 10 liters or 15 liters per minute if necessary. And then you can not even need a CO2 absorber, and you'll overcome this issue of rebreathing until you can replace that inspiratory valve. So that's a short-term fix. What about expiratory valve dysfunction? If it's stuck closed and the inspiratory valve is functioning, air could go in through the inspiratory valve into the patient, and when it tries to exit from the patient out the expiratory valve, if it's stuck in a closed position, there could be risk of barotrauma and pneumothorax. Usually it's leaky, however, and you can get that rebreathing pattern of an increase in baseline CO2 as evidenced here in the graphic. But notice the square waveform is somewhat maintained as opposed to the inspiratory valve malfunction. And again, you can increase your fresh gas flow to overcome this issue of rebreathing until the expiratory valve is replaced. Let's talk about vaporizer output next. The first concept has to do with vapor pressure and what's going on in the vaporizer. The vapor pressure of sevoflurane is 157 millimeters of mercury, and if you're at 1 atmosphere, sea level, that is 760 millimeters of mercury. So if you allow equilibration of a liquid in a closed chamber at sea level, you can see that at equilibrium, 157 over 760, the vapor percent will be approximately 21%. Well, if you delivered 21% sevoflurane to a patient, that would be an overdose in almost all cases. Well, all cases. And you need variable bypass vaporizer, 2 streams of inflowing fresh gas, one that bypasses the sump and another that picks up some of the gas to deliver the concentrations that we want to the patient. So let's look at this vaporizer output calculation in the case of sevoflurane, where we said the vapor pressure was somewhere around 157, 160. What would be present inside that closed chamber at equilibrium would be 21% sevoflurane. Therefore, again, the need for a variable bypass vaporizer. In the case of isoflurane with a vapor pressure of 240 over 760 at equilibrium, the gas concentration of that closed vaporizer would be 32%. Again, a need for a variable bypass vaporizer. Interestingly, 1 mil of our liquid anesthetic makes approximately 200 mils of anesthetic vapor. If you remember that concept, then you can figure out approximately how much liquid anesthetic you'll be using over time. For example, 100 mils of isoflurane will make 20 liters of isoflurane gas. Okay? And if you were administering 1% isoflurane at 2 liters per minute fresh gas flow, 1% of 2 liters means that 20 mils of that 2 liters of gas each minute is a volatile anesthetic, and 20 mils each minute times 60 minutes means there's 1,200 mils of gas each hour. Well, divide that by 200 mils of gas for each mil of liquid. 1,200 divided by 200 leaves you with approximately 6 mils of liquid isoflurane that you're using each hour. So if you remember the concept, 1 mil of liquid anesthetic makes about 200 mils of anesthetic vapor. You can have a general idea of how much liquid anesthetic you're using per hour based upon your fresh gas flows. The next concept has to do with delivery of inhaled volatile anesthetics at altitude. And this graphic that I've made shows isoflurane at not sea level in this case, but about 6,000 feet elevation, representing a higher altitude obviously than sea level, where the atmospheric pressure is no longer 760 but is about 610. Well, what happens? Remember that the vapor pressure of isoflurane is about 240 or so, and that at equilibrium at sea level it makes about 32% concentration above the liquid. At 610 atmospheric pressure, which is at 6,000 feet elevation, the vapor pressure of isoflurane doesn't change. It's still 240 or so, divided by 610 leaves you with about 40% at equilibrium, which means that your vaporizer will be putting out more than what you think it is. In fact, if you set the dial at about 2%, you actually are putting out about 2.8%. And 2% of 760 is about 15 millimeters of mercury, and 2.8% of 610 is about the same, which means that your vaporizer, the isoflurane vaporizer, is basically putting out a constant partial pressure, and it's partial pressure that's important for MAC, not concentration. We do not have to make changes on the dial as we change that vaporizer up to altitude, realizing that it'll put out a higher concentration but the same vapor pressure. This is different with the desflurane vaporizer. In this graphic, which I've designed here, it's showing a 10% desflurane on the dial. Remember that it's in its own environment of 39 degrees and approximately 1,500 millimeters of mercury, or 2 atmospheres. If you set 10%, it delivers 10%, but in this case, 10% of what? Not 10% of 760, what is at sea level, which would be 76 millimeters of mercury, but 10% of 610, the pressure at 6,000 feet elevation, which is only 61 millimeters of mercury. So you'd have to actually turn up the dial from 10% to about 12.7% to deliver the same partial pressure. So when you go up to altitude, you don't have to change the vaporizer dial for ISO or SEVO, because it's partial pressure, not the concentration, that is important. but you do need to change the desflurane vaporizer dial. You'd have to increase it to maintain the same partial pressure delivered when you go up to altitude, and you'd have to decrease it if you went to depth, i.e. down underwater in a submarine, for example. Don't think many of you will be delivering vaporized desflurane or isoflurane in a submarine, but it just illustrates the concepts of partial pressure and knowing vapor pressures. Let's move to CO2 absorbers now. One of the issues with CO2 absorbers is carbon monoxide, specifically with desflurane and somewhat with isoflurane. Desflurane is the main one where if you have a dry CO2 absorbent and a high temperature in it and high concentrations of des, and barrel lime used to be a worse actor. We use soda lime now, but still carbon monoxide can be formed in that dry CO2 absorbent. This is not being formed in the body per se. It is in the CO2 absorber in the presence of desflurane. In this hot alkaline environment, carbon monoxide is formed. And remember that our saturation monitors will not pick up this change in oxygen saturation, but we would have to actually get a blood gas and look at, with a co-oximeter, the SaO2, which would be decreased. Another problem with CO2 absorbers is compound A formation in the presence of sevoflurane. If you have low fresh gas flow rates, normally we use at least 2 liters per minute while we're using sevoflurane. High sevoflurane concentrations, high canister temperature, low water content, it's dry, then compound A can be formed. However, compound A in humans, even in patients with renal dysfunction, does not seem to be a big issue clinically. CO2 absorbents can get very hot, and sevoflurane is the classic one that can produce the very high temperatures in the absorber, more than DES and ISO. There have been case reports of a sudden decrease in delivered sevoflurane, a high temperature in the absorber. The patient may cough because of those blast, basically, of high temperature gases into their lungs, and then a fire occurs in the CO2 absorber. So sevoflurane is associated with CO2 absorber fires, rarely. If you're worried about the hydration of your CO2 absorber, and for example, you come into a room where someone left the fresh gas flow on over a weekend at 10 liters per minute or something, remember, just change out the CO2 absorber. Don't try to hydrate it with water or anything. And in the future, we may not have to worry about this when we don't have the sodium hydroxide and potassium hydroxide that degrades our volatile anesthetics. In the CO2 absorber, soda lime, heat and water are produced in the chemical reaction. And the smaller the granules, which is called the mesh size, the more area you have to absorb CO2, but the smaller the granules, the more resistance for gas flow. So there's a trade-off between area and resistance, and mesh size is what we talk about when we think about the size of those granules. Channeling refers to if you can get channels in the soda lime where like open passageways are present in the soda lime, the gas can preferentially go down those channels and you have less efficient removal of carbon dioxide. And as we previously mentioned, heat is an issue, especially with sevoflurane. High temperatures can occur in the CO2 absorber. Let's finish up with a couple miscellaneous machine topics. The first one is dead space in the anesthetic system. Dead space is actually from the Y connector distally, assuming that you have normally functioning inspiratory and expiratory valves. The corrugated tubing in your circle system, you can expand it or not expand it, even put a second corrugated tubing system when a patient's head away, for example. This does not contribute substantially to dead space, but dead space, as shown in the graphic in the bottom, assuming again that you have a normal functioning inspiratory and expiratory valve, is from the Y connector distally. However, if you put a humidivent in here, between the endotracheal tube and the Y connector, this does add to dead space. In pediatric anesthesia, this may be an issue of rebreathing. Now some safety systems associated with the anesthesia machine. The first is the diameter index safety system, is the wall source connector specific for a gas type. That is, the DISS system prevents you from connecting a nitrous blue line into a green oxygen source, as opposed to the pin index system, which is on the cylinders, which allows you only to match up proper tanks and proper yokes and prevents an incorrect cylinder attachment to the machine. Now there's some safety systems that we'll talk about next. The first is the proportioning system, which is the link between nitrous and oxygen flow meters, such that if you reduce the oxygen substantially at the same time that you're administering nitrous oxide, the nitrous oxide will drop because the machine will not allow the hypoxic mixture to be given to a patient. And then when you increase the oxygen flow meter back up, the nitrous oxide will follow it. So this is a proportioning system. As opposed to the fail-safe system, the fail-safe system is an oxygen failure cutoff valve, which is controlled by an oxygen supply pressure, such that if there is pressure supplied to the system, oxygen, you hope it's oxygen, pressure is being supplied, this allows other gases to be administered. But if the oxygen pressure drops for any reason, it shuts off or decreases the supply pressure of all the other gases in an attempt to prevent administration of hypoxic gas mixture. But if you think about this for a moment, if there was a wrong gas being supplied but it was pressurized, it could keep that cutoff valve open and allow that wrong gas to be administered. So it's a pressure that is controlling the system. So it's not really fail-safe. Let's look at leaks next, and then scavenging, and then we'll be done. Leaks. The low pressure circuit can have leaks, and remember that the low pressure circuit is the flow meters, and distally, well, the high pressure circuit is the tanks and the oxygen pipeline supply, everything up into the flow meter. So low pressure system, flow meters to common gas outlet. If the machine has an outlet check valve, then you need to use that little bulb and create a negative pressure, suck that open so that you can check this system behind the check valve. If the machine doesn't have an outlet check valve, then we just use the positive pressure leak test, where we pressurize the system and see if there's leaks in the low pressure circuit. The high pressure circuit, cylinder and pipeline supply pass the regulators to the flow meters. The flow meter order is with the oxygen flow meter last. Why is the oxygen flow meter last? So that if there happened to be a leak in any of the flow meters proximally, the last one would be oxygen, and there's a less chance of delivering a hypoxic mixture. We don't think much about the waste scavenging system, but this is the system that disposes of gases that are vented from the breathing circuit via the APL valve, if we're bagging the patient, or the ventilator spill valve, which goes then into this reservoir, which has holes in it so that we can have gas leak into our breathing around us, and occasionally we can smell gases if they leak out. But if the vacuum's set properly, we will remove the gas from the patient. This is called an open interface system. There's no valves, it's open to the atmosphere, allows positive and negative pressure relief from the holes in the top of the canister, and the vacuum flow rate must exceed the waste gas flow into it. As opposed to a closed interface system at the bottom right, it's close to the outside atmosphere and communicates to the atmosphere via valves. There's a negative pressure relief valve that protects the patient from the negative pressure of the vacuum, i.e. if you had a vacuum sucking gases out and it was very high pressure, potentially you could suck the gases right out of the patient's lung. While the positive pressure relief valve is there, it protects the patient from an obstruction in the disposal tubing. The patient's trying to exhale. If there was a pressure that built up, it could pop off this positive pressure and protect the patient from, for example, barotrauma. And then the vacuum control valve is adjusted to allow the evacuation of about 10 to 15 liters of gas per minute. Now, we went over multiple Anesthesia Machine ABA published keyword topics here during this discussion, and I hope that you have a great day. This is a picture from the Italian Dolomites on a bike trip that I went on this summer. Have a good one.